let's begin. Few people are still missing, but they'll come. So I'd like to begin with something which I myself was a bit confused, and maybe confused you guys also. This is regarding the binding energy per nucleon. This was from the last lecture. So the binding energy per nucleon increases up to iron, and then it begins to decrease. Okay, and here it sort of goes up and down because the number of neutrons, there are many isotopes are available. The number of neutrons can change, and therefore that can change the binding energy. So if you have, let us say, 3 protons and 2 neutrons, and you add 1 more neutron, okay, that can change the binding energy. Okay, so the confusion was caused by the fact that so what is the binding energy of a proton? 0. It should be 0 because there's nothing to bind. I mean, it's not flying away from itself, right? So binding energy of a single nucleon is 0. It is non-zero for deuterium, tritium, and so on. Okay? Because then now you are adding in more neutrons into this. So it increases as you go up, it increases up to iron. So, but when hydrogen gets converted to helium, the binding energy of the helium nucleus is higher than the binding energy of the 4 hydrogen atoms that formed it. Because those are 0 and this is some non-zero binding energy. Now, where does that binding energy comes? The binding energy comes entirely from what is called as the mass defect, which is the change in mass between the 4 hydrogen atoms or nuclei and 1 helium nucleus. Okay? They don't have, if you add up the masses, the 4 hydrogen atoms have a higher mass than the helium nucleus. And that loss of energy is called the mass loss of mass is called the mass defect. That converts to energy as delta mc square. Part of that energy goes into providing binding energy for the helium nucleus, and part of it is released into the as gamma ray photons. So this is how the energy balance inside that proton-proton chain works. So indeed, the helium nucleus, etc., have higher energy. Helium-4 is over here, and there's some fluctuation over here because the number of neutrons vary. And then it sort of stabilizes. And the other thing to note is up to iron, you can form elements by fusion, because fusion remains a exothermic process. After this point, because the binding energy per nucleon starts going down, even if you fuse atoms together, you don't get any net gain of energy. The process becomes, after this, up to this point, fusion is the preferred way. And beyond this point, fission is the preferred way because the product is more stable. It has a lower energy than the source. And so because of that, over here, of course, fission operates, and over here, fusion operates. Okay, so now coming back to our discussion on white dwarfs. So we said last time that one of the ways of direct detection was to just take an image. And I told you that one can take an image of a white dwarf directly. So this is a white dwarf, which is around the brightest star in the sky, Sirius. And there are several other such white dwarfs that have been discovered. They're very faint, so they're not very easy to see. Yeah. But if you take images of Sirius multiple times, you will see this object orbiting Sirius. Sirius is a somewhat more massive star, not very much more massive. It is only about 2 or 3 times the mass of the sun. And I think this must be at 0.6 mass, solar masses. So the mass difference is not very huge, but the luminosity difference is huge. Okay. So now when you have binary star systems like this Sirius system, you form what are called Roche lobes. Okay? And they are defined by something known as a Roche potential. And it's basically the gravitational potential of in a rotating frame. And the Roche surface are equipotential surfaces. And these are critical equipotential surfaces where the potential is equal. So suppose you have two stars going around each other. These are binaries in an orbit. They will each form their own Roche lobe. And the radius of the Roche lobe will be dependent on the mass of the star, right? Not on the radius, but only on the mass of the star. And of course, it will also depend on the separation between the two stars. And a less massive star will have a smaller Roche lobe than a more massive star. These are not spherical systems because the system is rotating. So they have a slightly teardrop kind of shape. They're not spherical in shape. And they intersect at the Lagrange L1 point of the system. Okay. So now, interesting thing begins to happen if one of the stars becomes bigger and fills its Roche lobe. So when can it fill its Roche lobe? Typically when it goes into the red giant phase. We know that the sun's radius is going to increase by like several hundred times when it goes into the red giant phase. And when that happens, the sun, if it had a binary, relatively close binary, it could have filled up the Roche lobe, right? But it doesn't have a binary. So in the case of the sun, that's not going to happen. But there are a large fraction of stars in our galaxy are actually binaries. And when they're binaries, and in some particular situations, interesting things happen. But before we go there, so one can work out this whole thing analytically, but it's quite complicated. So Eggleton in 1983 in a paper gave a formula for calculating the Roche lobe radius. Okay, and this is a function of course, the separation between the two binaries, but it is also a function of their relative masses. So if you know M2 over M1 and the absolute value of the separation, then you can plug in to this equation and get a reasonable value for the Roche lobe as a function of the separation. Okay. So now why are these Roche lobes interesting in the white dwarf context? They're interesting because if there is a binary stellar system in which one of the stars is a white dwarf and the other is a normal star, then one can have a situation that leads to what is called as a type 1a supernova. It's caused by accretion of matter from a normal star onto a white dwarf companion. Luminosity is in a relatively narrow range, calibratable from the light curve. Okay, so why does what will happen? So what happens is if the Roche lobe of if a star fills up its own Roche lobe, then the material that is exceeding the Roche lobe actually cannot stay bound to the star and begins to flow onto the other star. Okay, so over here, go back to our Roche lobe diagram. Suppose this star becomes red giant and fills up this Roche lobe, then material will start flowing like this, and like this through this point onto this star. Now, suppose this star is a white dwarf. What's going to happen? What's going to happen? Sorry? Yeah, the mass will exceed the Chandrasekhar limit. Okay. And what will happen when that happens? There will be the whole thing will become unstable. Okay. it will usually what happens is that there is a very giant explosion. So whatever material has been accreted cannot now be supported by the degeneracy pressure of the electrons in the white dwarf. So it just explodes. The whole white dwarf explodes. And depending on the exact conditions, the white dwarf may destroy itself. Okay? In some cases, it doesn't destroy itself, but we won't go into that. But that is the type 1A supernova explosion. So I'll just show you. Huh? It flows from whatever fills up the Roche lobe. It need not be larger versus smaller. Whatever fills up the Roche lobe. So it has nothing to do whether it flows from large. It can flow from smaller to larger if the smaller one fills up the Roche lobe. And the Roche lobe filling typically happens in the late stage evolution when it goes into the red giant phase. So this is what happens. So that everything is gone. Sometimes the explosion can even destroy the neighboring star. Sometimes not. So these two stars are rotating. This is a white dwarf. This is called as an accretion disk, which forms around the white dwarf, and material is flowing from through the L1 point straight onto the everything happens in sort of one plane. The accretion disk is in the same plane as the plane of the revolution of these two stars, and then this leads to a giant explosion. Huh? Because see what happens in a white dwarf. White dwarf is in equilibrium because gravity is balanced by the electron degeneracy pressure. Now, if no material is accreting from outside, gravity stays the same, electron degeneracy stays the same. So there is no change in the radius of the star. But now if you start throwing material onto the star surface, what happens to the gravity? Effectively, you're increasing the mass of the star by throwing material onto it. At some point, that mass is going to exceed the Chandrasekhar limit. And when it exceeds the Chandrasekhar limit, because it is in some other circumstances, it may have formed a neutron star. But in these circumstances, this accretion leads to a sort of bounce and an explosion. Yeah. So that's the reason it does not form a neutron star, and it leads to this.
Is the time scale of this event?
I'll show you a light curve that will make it clear. So it's coming in a minute. Is it? No, wait. Yeah, no, it's coming in a bit later, huh? That usually doesn't happen because white dwarfs will have a reasonably large Roche lobe and a very small size, right? So it's very hard see, white dwarf is only 10,000 kilometers in size, but it has a Roche lobe comparable to the sun. If it is, let's say, a solar mass white dwarf, it will have a Roche lobe which is the same size as the sun. And so it cannot fill up like that. Yeah. Because see, why is that other star filling up its Roche lobe? Because something is happening in its core. Fundamentally, something is changing. So it is going into an unstable state as a red giant because hydrogen fusion has slowed down or stopped in its core. And that is the reason it puffs up like that.
So it's filling up this Roche lobe where the Roche lobe radius is from the original star, not the growing size.
No, it's from the growing size. So the Roche lobe also changes.
If Roche lobe is also increasing.
No. Roche lobe or what? No. Let's go back. Suppose this is the white dwarf. Okay. This is the normal star. This white dwarf will just stay there peacefully. It's not going, nothing is going to happen to it. Its radius will not change, its mass will not change. However, this guy can go into the red giant phase. And it is this star which is filling up this rho slope.
So when it's increasing its size,
Huh.
its rho slope will stay the same.
Will stay the same because until it fills up, because the mass is not changing, right? The rho slope doesn't depend on the radius of the star. It only depends on the mass of the star. So as this guy expands, okay, in fact, the rho slope may become slightly smaller. For example, while it goes into the red giant phase, the star can shed some of its mass. Not a huge amount, but fraction of its mass, 10-20% of the mass can be lost when it goes into the red giant phase. So the rho slope could shrink. Okay, but in general, in the simplest case, let's say it just puffs up and there is no change in the rho slope radius. And the moment this star grows big enough to fill this rho slope sphere, it will start flow. Okay. So why are white dwarfs important in astrophysics? First is cosmochronology, age dating of stellar populations. Okay, what does that mean? So suppose I give you a galaxy, some galaxy, and I tell you that, oh, there are a very large number of white dwarfs in that galaxy. What does that tell you about the stellar population in that galaxy? Does that galaxy have an old stellar population or a young stellar population? Young. No, actually old, but now tell me why old. Correct, correct. So, correct, absolutely right. So what she says is absolutely correct. So what happens is lower mass stars have long lifetimes, and it is only, we saw that higher mass stars will form neutron stars or black holes. Lower mass stars are the ones who form white dwarfs. So if you're seeing lots of white dwarfs, that means the lower mass stars have evolved into white dwarfs, correct? That means this can only happen, this cannot happen in 100 million years. It can only happen in 5 billion years, 10 billion years, 15 billion years, like that time scale. So if you're seeing a lot of white dwarfs, that indicates that you have a substantial old stellar population such that lots of low mass stars have converted into white dwarfs. So that allows you to do age dating. Its cooling sequence can be used as a cosmic clock. We saw last time how the luminosity changes as a function of time for white dwarfs. Type 1a supernovae are very, very important because they are standard candles for cosmology. They're the most important distance indicator used in cosmology. Why are they the preferred distance indicator? Why not Cepheids or something else? Huh? They're very bright. They're very luminous compared to Cepheids. So which means type 1a supernovae can be seen to the other side of the universe. Cepheids can only be seen in relatively nearby galaxies. There's also the problem of resolving the Cepheid, finding it and measuring only its light. Because if its light is buried in the overall light of the whole galaxy, you will never be able to detect them. So Cepheids are very poor indicators for cosmology. This led to the discovery of the accelerating universe. So they went and measured the brightnesses of very distant type 1a supernovae, and they were discrepant from the model. And then they said, okay, the model itself has to be changed. And they said the universe is accelerating. Right now it's accelerating. Yeah, it was decelerating many billion years in the past, but right now it's accelerating, and acceleration will continue to increase in the future. This led to the award of a Nobel Prize a few years ago. Binary evolution. So one can study binary evolution. So these kind of variables are known as cataclysmic variables. Any variable star that ends up in a big explosion, okay, is called as a cataclysmic variable. And the most common type of cataclysmic variable is the type 1a. they might also manifest as X-ray binaries. Okay, low mass X-ray binaries in general. Why? Because when that accretion process before the supernova explosion happens, type 1a happens, before the type 1a happens, what tends to happen is that there's an accretion disk formed around that white dwarf, and as material falls onto the white dwarf, it due to friction, dynamical friction, it gets heated up, and it can get heated up to a temperature where it will begin to emit X-rays. So individual X-ray binaries can be seen with a high resolution X-ray telescope. And sometime later, I'll show you images of that. And those X-ray binaries are caused as precursors to the type 1a supernova event. Now, is it that, okay, if you see an X-ray binary, you should keep staring at it for a supernova to happen? No, because timescales are long. It may take 100,000 years before it becomes supernova. All depends on the accretion rate and so on, and what is the mass of the white dwarf to start with. Okay, planetary systems, evidence of past and present planetary systems. Okay. Past planetary systems, because, see, take the example of the sun. Okay. Right now, it's not a white dwarf, but when it becomes a white dwarf, what will be the planetary system of that white dwarf? It will be Jupiter onwards. Okay, up to Mars, everything will be swallowed up by the red giant. So we will have a present planetary system at that time, and maybe there will be some evidence, we don't know, of a past planetary system, right? Because it's an evolved star. Remember, white dwarf means this has come out of a star that has been in place for many, many years. So it's like it is like a person who's died at a very old age. You can be guaranteed that this person died very old. So the star has to be old for it to die as a white dwarf. Okay. Insights into late stages of planetary evolution. Why late? We've just answered that, because white dwarfs are old. Neutron stars. Okay, we move on. Now, white dwarfs are old, but neutron stars, do they have to be old? No, they can be old, okay, but they need not be old. They can be old, they can be young also. So these neutron stars are a result of another kind of supernova, which is called as a type 2 supernova. The type 1a was supernova only happened because of that mass accretion. Without mass accretion, if there's a white dwarf like the sun without a binary companion, nothing will happen to it. There's no type 1a. Okay? But if you have a massive star, say in this mass range, then that can lead to the formation of a neutron star. So what are the steps for forming a neutron star? First of all, one thing happens, I have another slide later on, is that what begins to happen in very massive stars is that the core will obviously be hottest. And outside there will be layers which are cooler and cooler. The core becomes so hot, okay, that it can fuse elements into iron. So you can have an iron core. Surrounding that, you may have a core of a slightly lower atomic number. Then slightly lower, slightly lower. So this is called as an onion shell model. So you could have progressively different layers where fusion of different elements is going on. And in the outermost layer, you will have hydrogen. Innermost layer, second layer, you will have helium. Third layer, you will have something else. This carbon, nitrogen, oxygen, all of those layers will be there. Inside, in the core, you will have iron. Now, once a substantial iron core is formed, what's going to happen? Fusion will stop because nothing beyond can be fused. So iron core itself can sometimes hit the Chandrasekhar limit. Okay. And if it hits the Chandrasekhar limit, it's going to collapse. Okay? And when it collapses, there is a process known as neutronization that happens, which means protons and electrons come together and they form neutrons. So this process happens on a very massive scale. And there can be again a bounce because the outer layers are still fusing, inner layers have fusion stopped, core collapse is happening, and so on. And this leads to a explosion, a bounce back and an explosion, resulting in a powerful shock wave accompanied by massive emission of neutrinos. Okay, and there was many years ago a supernova discovered in the Large Magellanic Cloud, which was this kind of supernova. And we actually detected, even in a few years later, we detected neutrino emission from 1987. Okay? And then because of the bounce back, there is a ejection of the outer layers. So although you may start with something in this mass range, the remnant that you will form may not be in this mass range. It will be lower in general. And that leaves behind a hot, rapidly rotating neutron star. Okay, we'll come at why it's rapidly rotating in a minute. But this ejection of outer layers, etc., leads to the formation of a very, very compact object. How compact? Remember, I said white dwarf is about 10,000 kilometers. This is 10 to 14 kilometers. So it is 1,000 times smaller than a white dwarf. It is more massive. Okay, because it's 1,000 times smaller, it should be 1,000,000,000 times more dense. Okay, at the same mass. And mass is typically in this range. Okay, obviously, it has to be greater than the Chandrasekhar limit. And it usually doesn't exceed this. Now, here, unfortunately, there is no strong boundary. Okay? We know at what mass an object transitions from white dwarf to neutron star, but there is no equivalent limit for the transition from neutron star to black hole. And why that is so, we will come in a minute. And partially you get the answer here, is that the neutron star is an incredibly complex object. Okay, because it has an outer crust which contains of nuclei and electrons, an inner crust which contains neutron-rich nuclei and some free neutrons. Outer core is neutron superfluid plus protons plus electrons, and the inner core could be some exotic matter. Okay, we don't know exactly what it is, but the whole thing is supported now by neutron degeneracy pressure. So in some sense, the neutron star is like one giant neutron because the protons and electrons can't stay separate. They have all been pushed into the nuclei. So there is it's a collection of nuclei only. There are no except in places where you can have protons and electrons floating around. Otherwise, it's just one giant nucleus. Yep. So this is a graphical illustration of what I just said. Outer crust, ions and electrons. Inner crust could have an ion lattice with superfluid neutrons. Then there are superconducting protons. Okay, the inner core, of course, is unknown. Okay, and the densities can go up to this value, but this is 2 times nuclear density. This is comparable to nuclear density. And then at these densities, there's something known as neutron drift, which happens, which I don't know exactly what it is. And there is even a thin atmosphere consisting of hydrogen, helium, carbon, and a few other elements. So because of this, there's a lot of trouble. Why is there a lot of trouble? What is the main problem? How did we obtain the Chandrasekhar limit? the Chandrasekhar limit used the fact that there are relativistic degenerate electrons, and there may be non-relativistic degenerate electrons or non-degenerate non-relativistic electrons and so on. So it's a combination of all of these factors which is producing that electron degeneracy pressure, which is balancing the gravity. Okay, and why were we able to solve for the Chandrasekhar limit? Because whatever be the composition, we knew the equation of state of a degenerate electron gas, non-degenerate equation gas, everything we knew, right? And therefore, we could solve that equation. But here, we don't know the equation of state. And that is and why we don't know the equation of state, again, we can come to. But before we go there, extreme density, is, remember, is 1,000 times smaller. So it should be about 1 billion times more dense. So we know white dwarfs have about 10⁶ grams per centimeter cube. This is 10⁻⁵. Rapid rotation, time periods from milliseconds to seconds. So the millisecond part, leave out for the moment. But the second part is caused by the fact that you are shedding all kinds of matter. You are shedding angular momentum, but not all of it. But you're reducing the radius also. Okay? And when you reduce the radius, the thing starts spinning faster and faster. Right? The omega of the star will increase. And this star has gone up from a size larger than that of the sun to 10 kilometers. And because of that, it can rotate. It typically rotates of the order of seconds, 1 second period, 2 second period, like that. Equation of state, it relates pressure to density. It also allows you to calculate the mass radius relationship. Okay, and we can do both of these things with white dwarfs. But in the case of neutron star, this is an active area of research. People are still trying to figure out the equation of state of a neutron star. The maximum mass could be in this range. It's a little bit equation of state dependent. Okay, so why is there such a big problem with determining equation of state? So first of all, extreme conditions not reproducible in any lab on Earth. And this is a quantum many-bodied problem. There is uncertainty in the composition of the inner core. Okay? Nevertheless, various kinds of observations have been made which can constrain various parameters for the neutron star. So the mass can be constrained by observations of binary pulsars. Okay? So the most famous binary pulsar is what is known as the Hulse-Taylor pulsar. And some people observed it, Hulse and Taylor observed it for 20 years. And they determined that the change in the orbital parameters of this binary pulsar means two pulsars orbiting each other. Okay. The change in the period, the change in the orbit of these binary pulsars was exactly commensurate with the expectation of the loss of energy from gravitational waves being produced by that system. And so that was a sort of indirect way of detecting gravitational waves. And they got the Nobel Prize for that many years ago. But they did 20 years of observations to establish this. Radius estimates can be done by X-ray bursts. Okay? Because remember that accretion disk, etc., all that can form around neutron stars also. And there can be X-ray bursts from these things. And cooling curves. So you can also try to establish what is the pattern for cooling of these stars, and that can help you constrain the radius. And of course, gravitational wave observations. So far, we have observed only one neutron star merger for sure. Although there have been many black hole mergers that have been observed via these gravitational wave observatories. So in the future, if this becomes very routine, then that may also help. Okay. So now we wrote down some time ago. Yeah. They exhibit superfluid properties. You know what are superfluids, right? Like superconductors. They're fluids that can sort of flow out of the container by themselves. So they're very strange systems. So neutron star is like the condensed matter physicists' dream come true, because everything that condensed matter physicists like to study and understand, all of that is happening in one place. Right? Except that you can't really see it. I mean, if they could go to a neutron star and observe it closely, directly, or produce a neutron star in a laboratory, their problem would be solved. Okay, anyway, so that's what is meant by superfluidity. So when we wrote down the equation of hydrostatic equilibrium, that was very simple. But because what we were doing was we were saying radiation pressure is being balanced by gravity. Okay. So now again, you can write it in that sort of Gm over R square form with the pressure gradient over here, except that in the case of the neutron star, we remember when we wrote down hydrostatic equilibrium equation, we ignored three things. Okay. Anybody remembers what those three things were? Magnetic field. We ignored the magnetic field. What else? Huh? General relativity. So we use Newtonian mechanics. One more thing we ignored. We ignored the fact that the star could be rotating. So we ignored so we said for a non-rotating star, in the absence of a magnetic field and ignoring general relativistic effects, we can write down the equation. Here, of course, you can't ignore general relativistic effects because the gravity is so strong that GR dominates. So you can write this kind of equation. So this is known as the TOV equation. After Tolman, Oppenheimer, and Volkoff. This Tolman, if you've seen the Oppenheimer movie, then Tolman and Oppenheimer appear in it. Volkoff was a PhD student of Oppenheimer at Berkeley. And so they wrote these papers in the late 1930s. So actually we knew about neutron stars should exist and what should be the equation for hydrostatic equilibrium, etc., as far back as 1939. Yeah, because they were not discovered until 3 decades later. We'll come to that. So this is the way you can write it down. You can rearrange this equation. You write it in this format. Okay, so you write it in your usual Gm rho by R square kind of format. But now here you have three terms. 1, 2, 3, and if you start putting c equal to infinity over there, then the second term in each of these equations disappears, and you're left with 1, 1, 1, and you will get the classical Newtonian limit, which is this equation. So the first correction, this term, which appears in relativity, takes into account the impact on pressure because of relativity, general relativity. This takes into account the fact that the enclosed mass has to be recomputed using general relativistic formulation. And the third correction takes into account an effect known as gravitational redshift. So what happens is if you have any particle coming out of or any photon coming out of a strong gravitational field, then it encounters what is known as gravitational redshift. So the energy of the photon decays because of the gravity. So that effect is accounted for here in this last term, and together you have so now this obviously, see, in the case of the hydrostatic equilibrium equation, okay, we could trivially solve it because we could write down the equation of state. So if we said that the outer part of the sun, it's like a ideal gas, So I'll just use ideal gas equation. That gives me my equation of state for the system. And you can solve it. But here, because the equation of state is unknown, which means we cannot write rho in terms of P or P in terms of rho, that this equation becomes intractable. And how intractable? So what is shown here is, this is from the book by Kippenhahn, the radius in kilometers of the neutron star. And this is the mass of the neutron star. So there are now degeneracies between mass and radius. Okay, you can't, unless you determine one, you can't determine the other. And these are different, each of these curves represent different equations of state. So I think, if I remember correctly, the non-interacting neutron gas is what was calculated by Oppenheimer and company. Okay, and they got this equation of state. They assumed the equation of state and they got this mass radius relation. But now other people said, no, it's interacting neutron gas. And they did this. Then somebody said, no, the equation of state is something else. It's something else. It's something else. So this whole region of the parameter space is getting filled up with different curves with slightly different assumptions for what is the equation of state of a neutron star. If you could determine it in some other independent way, then this would collapse. What is this line? Schwarzschild radius. It corresponds to the Schwarzschild radius of a black hole, of a non-rotating black hole. And if you go beyond that, it will become a black hole. So therefore, none of these curves can cross this line. Yeah. So quite a mess. So this is as far as sort of, we've looked at neutron stars as completely theoretical objects so far. Okay, we using our knowledge of quantum mechanics, condensed matter physics, everything we know, we throw it in and so on. However, pulsars, neutron stars can be observed, and they can be observed in the form of pulsars. Okay, so these are highly magnetized rotating neutron stars, and there is something known as the lighthouse model. So the model is a very simple one. We know the neutron star is rotating, but assume that the magnetic field and the rotation axis, the magnetic field axis and the rotation axis are not identical. What will happen when that happens? The particles will be expelled from the magnetic field. But since the rotation is happening, it will create a lighthouse kind of effect where the beam of the particles streaming out of the neutron star will cross our line of sight periodically as it rotates. So typically twice every rotation it will cross, right? And you will get beamed emission along the magnetic axis, and this will be observed as periodic pulses. So thousands of pulsars have now been discovered since the first discovery in 1968. Most of them are what are called radio pulsars or normal pulsars. Some of them are called X-ray pulsars. So these are typically in binary systems, and now there is accretion that is beginning to happen onto the neutron star, right? These are not very common. They're much rarer than the radio pulsars. And then also rare are the millisecond pulsars. And these are caused by, again, they're typically in a binary orbit. And they are caused by transfer of angular momentum from the neighboring star onto the to the neutron star, which is rotating. And that can lead to a speed up of the rotation of the neutron star. And this leads to millisecond pulsars. So what are typical pulsar properties? Their periods range from 1 millisecond to 10 seconds. There's a spin down rate. Okay. So pulsars obviously don't keep spinning at the same speed. Why do they slow down? They're ejecting mass, yes, but they're also ejecting energy. So the angular momentum of the system has to go down. It slows down over time, just like the Earth's rotation is slowing down over time. Neutron stars are slowing down. By how much? 10 raised to minus 21 to 10 raised to minus 12 second per second. Their magnetic field is very strong. Okay? And it's of the order of 10 raised to 19 Gauss, assuming, no, it's not of the order 10 because the P dot is not 1. P can be of order 1, but P dot is. You have to plug in the correct value and get the magnetic field. We know it's up to 10 raised to 15 Gauss or so. Characteristic age can be calculated from its period and its slowdown. Okay? Because if you say that it's continuously slowing down, there's no speed up like in the case of millisecond pulsars, then initially when it is spinning fast, its P dot will be higher and P will be short. Later on, as it slows down, then the rate of slowdown also slows down. So the P becomes high and the P dot becomes low. And so it changes in a very systematic way. So you can, by giving, suppose I give you the this P over P dot for 2 pulsars, you should be able to guess which one of them is older and which one of them is younger. Okay. So very often a P dot diagram is used by all pulsar astronomers. So they will plot log of the period on the x-axis and the log period derivative on the y-axis. And so there are various pulsars of various kinds. So all these guys are your millisecond pulsars. Okay. There are special kinds of stars which we won't talk about, which are called magnetars. Magnetars have very long periods and very low periods, very large period derivatives, but they are extremely highly magnetized. So the magnetic field of these guys is 10 raised to 15 Gauss. And over here, it could be like 10 raised to 9 Gauss onwards. But these are million times more magnetized than these are. Very exotic objects. Now there is something known as the death line. What do you think causes that? What that means is there are very few pulsars with very long periods. And they will obviously have a very small period derivative. But let's look at it along the x-axis. There are objects which have pulsars with very long periods are not found. Why is that? Pulses become weaker and weaker and they're not visible. That's correct. But why? Suppose you take a very big magnet and you start spinning it around itself at high speed. What is it going to produce? Huh? It will produce current. It will produce an electric field. It will produce current. Okay. And this whole pulsar phenomenon is basically charged particles being accelerated in some kind of an electric field. And that electric field is created and sustained by the rotation of the star. Now, if the rotation slows down, then the strength of that electric field becomes weaker and weaker. And then you can eventually a point comes where it's just too weak. It's not that it's not rotating. It is still rotating. It's not that it is not radiating, but the radiation is so weak that our telescopes are unable to detect it. And that leads to this kind of death line. I don't know what these INS objects are.
So does the death line move as our instruments get?
Yeah, they could move. But remember, we can't go very much beyond because our sensitivity is improving by, this is all log scale over there. So yes, it could improve if your sensitivity becomes really very high. Then, so that leads to an interesting story. So the Chinese have built a very, very large telescope called FAST. It's located in southern China. It is a giant dish. So the previous giant dish was Arecibo, which was 300 meters in diameter. The Chinese have built a 500-meter diameter dish. Now this thing is super sensitive, super sensitive. Okay, so it has really moved the deadline. Okay. However, there's a problem. Because this is a single dish, it doesn't have very good resolution. So the positional error of the pulsar on the sky is very high, right? So normally what people do is that they do a very quick scan of the sky and they find some rough area where pulsars are found. You can do that with a single dish telescope also. And then you follow it up with a high resolution telescope like VLA or GMRT. And then you see that, okay, that's called localization of the pulsar, because now you have much better resolution. You know what is the period of the pulsar and so on. You just don't know where it is exactly. So you can search the parameter space and locate the pulsar. Okay, it's exactly at this coordinate. Now with FAST, no follow-up is possible. Why? Because the sensitivity of FAST is so much higher than that of GMRT. Like if FAST guys tell you that somewhere in this region there are 7 pulsars, okay, they're all very faint. Yeah, but this is the period of the pulsar, you find them. Our guys go and look, they don't detect those pulsars at all because our deadline is somewhere else. We are not sensitive to that very low emissions, very faint emissions. So this is a very peculiar problem. And the Chinese don't know, they can't even see, because normally the way it works is you first find out which rough area of sky the pulsar is located. Then you localize the pulsar. Okay. Then you can write a paper saying that, okay, I found this new pulsar at this position. And then you can study that pulsar for 5 years, 10 years, and write many papers about it, about its detailed phenomenology. But here, step 2 is not happening. So the Chinese are not able to even publish papers of the pulsars that they have discovered. And they're discovering them in the hundreds and the thousands, but they can't do anything with it. Neutron star observations. So radio observations are the primary method for detecting pulsars. And dispersion measure gives the distance estimate. So the dispersion measure is commonly used as a proxy for the distance to the pulsar. So what happens is, because of dispersion, the arrival time of a pulsar is of a pulsar signal is a function of frequency or wavelength. Okay, and by measuring the delay in arrivals, one can measure this quantity. But that quantity is an integral of the electron density times the distance along the line of sight. So you integrate any dl from Earth to the pulsar, and that will give you the electron density. Now, if any were constant, you could pull it out of this. And then you directly get the value of the distance to the pulsar. But unfortunate part is any is not constant. Depending on the direction where you're looking, the electron density can go up or down. We have some rough idea of what value it has in different directions. And therefore, you can get a rough estimate of the distance. But you can never get a distance unless you can measure the distance in some other way. Like it's in a binary orbit, and then there is a star that's associated with it, whose parallax you measure with Gaia or something like that. I'm not sure whether that is being done, but directly you can't measure the distance of a pulsar from the radio. But you can measure the dispersion measure. X-ray observations are caused by thermal emission from the surface. Okay, so very energetic system because of the strong magnetic field. Things that don't happen on Earth. See, on the Earth, the magnetic field just shifts your compass. Okay, it doesn't change our lives, right? But on a neutron star or close to a neutron star, the magnetic field is so strong that many effects that we are not used to manifest themselves. Then X-ray pulsars are sometimes seen in binary systems because that's I said, there's a pulsar, it's in a binary orbit. There is Roche-Loeb filling from the binary, and now material is accreting onto the neutron star. Gamma ray observations can give you an estimate or measurements of the magnetospheric emission from the neutron star. And there is a telescope known as the Fermi telescope, which has discovered a large number of gamma ray pulsars. So the people who first, these are Fermi pulsars, which are then followed up in the radio and so on. And of course, gravitational waves. There has been one neutron star merger that has been followed up. It has got this number, gravitational wave. This is the date on which it was detected. Okay. And this is the most well-studied gravitational wave event ever in history. I mean, they had one discovery paper which had 3,500 authors. This is the biggest author list in all of astronomy, in the history of astronomy. And that these can potentially provide constraints on the neutron star equation of state, because you can literally model the decay of the orbit very, very precisely from the amplitude and the period changes of the gravitational wave signal. So this is an area that is in its infancy at the moment, but if in future years as more detectors come online and the detectors become more sensitive, we might see lots of these. Okay. So there are these magnetars which we saw there on that PP dot diagram. They're extremely strong magnetic fields. Many of them are what are called soft gamma ray repeaters. What does that mean? Any guess? Soft gamma repeaters. What would that mean? What does soft mean? Forget soft. Repeater is easy. Okay. So they repeat periodically, or at least they start and stop periodically. So they're emitting gamma rays today. They emit for the next 5 days. Then they switch off. And then some days later, they turn on again. So that's what is meant by repeater. What is soft? Huh? Period is low. No. Soft means usually lower energy. So very often you will encounter this in X-ray astronomy and gamma ray astronomy. The soft X-rays, hard X-rays, and so on. What soft X-rays means is within the X-ray band, relatively low energy X-rays are called soft X-rays, and hard X-rays are high energy X-rays. So similarly, soft gamma ray repeaters means within the gamma ray band, which is higher energy than X-rays, soft gamma rays are relatively low energy gamma rays. Anomalous X-ray pulsars. Okay, so these are again things that whose X-ray emission can change over time and so on. So these are a different category. And it is also hypothesized that quark stars may exist. Core is composed of some kind of quark matter and possibly strange quark matter, but there is no real observational evidence for the existence of these kind of quark stars. So why are neutron stars important in astrophysics? They are the testing grounds for extreme physics. Okay. Quantum chromodynamics. Okay, so which is all these quarks and study of all those kind of objects. Then the strong strong force and so on. And one can also study the general relativity in the strong field regime. They're very precise timekeepers. So they rotate at a certain pace, keep on rotating at that pace, and very, very slowly they lose time. Okay? We saw that they lose like at 10 raised to minus 12 second per second or slower. Okay, so they get very, very stable timekeepers. And therefore, they can be used in the Hulse-Taylor binary, which I mentioned. They can be used to study the decay in the orbit of these pulsars over time. Of course, potential for gravitational wave detection through their mergers. In binary systems, they produce X-ray binaries, and they can be sources of gravitational waves detectable when the binaries come close to a merger. Nuclear physics can be studied, constraints on nuclear equation of state, and insight into behavior of matter at extreme densities. So neutron stars, I think if you take one topic in astrophysics where the traditional high energy physicists or particle physicists, okay, or nuclear, atomic and nuclear physicists are all interested, is neutron stars. Because they give them access to a region of the parameter space that they have no hopes of ever exploring in the laboratory. Okay, so I think we can stop here. We'll continue next time. We move on to black holes. Again, as always, I'm just giving you an introduction. I'm just introducing you to the jargon and the overall big picture. Each of these things will be gone into more detail in various courses.